Hello everyone, welcome to Learn Overflow. In this video, we'll discuss today's LeetCode problem, that is the power of 4. So this is the easy level problem, and we'll understand two, three ways of solving this problem. One obviously would be a loop which you can solve. The other will be a bitwise operator to solve this kind of question. Remember, I will make sure that you understand the bitwise operator and every bit of that process of how you do that. So that will be our process in that question. And before moving on, if you haven't subscribed to this channel yet, make sure to subscribe to Learn Overflow for regular lead code videos like this. The question says we are given an integer n, that's the integer n given to us, and in that we need to return true if it's a power of 4, otherwise return false. What that means, we are given n as 16, it's true because it's a power of 4, like 4 fours is 16. And it is given like 5, it was false because it's not a power of 4. And further we see that there's like n equals 1 and that becomes true. It's because, why is it so? The main idea is 4 to the power 0 is 1. So that's the why it's like true is possible. Okay. Now the first approach for us would be to go ahead with a bitwise operator. So in the bitwise operator, we need to do two, three things. If our bitwise operator, see, 4 to the power -1 -2 is not something we are looking for. Okay, because if look, the constraint is it can go up to -2 to the power 31. So negative numbers can be a value for us. But if there's a negative number, is there power of 4 possible in that? Obviously not. So will we do in this case? Say we'll first check for us will be to see that it's not a negative number. So we'll check n must be greater than 0. Okay, the next check for us would be to check if it's a power of 2 or not. Okay, so if it's the power of 2, then we need to investigate more to figure out whether it's a power of 4 or not. Fine. So that's the whole idea behind this. Now how will we go ahead with that? We have simple stuffs like let me just write this code as well at the side by side to make you understand what exactly which part did, because this is a like bitwise operator. So I will explain is bitwise. So first, let me just write it fast. Okay. So for that, we first will simply go ahead with return. First check is num greater than 0. We just kept to check whether our num is greater than 0 or not, and then we'll check our num is power of 2 or not. So for that, we'll simply say num and num minus 1. So if num and num minus 1 are double equals 0, so that means it's a power of 2. I will explain it to you how this exactly works for us. Okay, I will explain that. Give me a minute. So and further we'll make more checks in the way. We'll investigate whether num and our particular bit mask is 0x. We have how many digits? We need to go up to 2 to the power 31. So for the 2 to the power 31, we need 8 bits. Okay, 8 masking bits. So that would be 555555555. Okay, so that should be 8 fives. Yeah, I guess so. If this whole thing is equals to our num, then it's a power of 4. So this should work pretty well. Let's check this out whether it works or not. Sorry. I went ahead with num and it was like n given to us. So let's just change that, and over here you see, yes, it works pretty well. So if I just try to submit it, let's see how fast or slow this whole thing is. This is a 1ms solution, and you can see the 100% faster solution. Now let's try this. Just try to understand this or break this down into each of the parts. Okay, now when it says num and num minus 1 double equals 0, so what that exactly means? Say, and I just write down two numbers for you. Now the two numbers say we have first we have 2. Okay, for that say we have if we're going ahead with 2, then we have something like 0 and then 8 bits, sorry, and 0. Oh, well, yeah. So it's like 0 and further it should be like 0 0 1 0. So that's power of 2. Okay, so what we're trying to understand, whether this is the power of 2 or not, right? So this is we all know that this is true in decimal, right? This is a binary, this is in decimal. Now what we're trying to understand over here, we want to understand whether it's a whether it is a like how we are finding out that. Oops. we want exactly to find out how our particular approach is working over here. Fine. How it is working. So let's say what we want to do, we want to just check over here that a particular approach that we have over here. Let's check how this works. Say we have this one as a 2. So this is the minus 2. This is 2. Okay, so that's positive. Just make sure. What this works? So when we're doing num and num minus 1. So what is num minus 1? Num minus 1 would be something like this: 0 0 0 0 0, and then that would be a 0 0 0 and then 1. Fine. So what will it do if we do a and of that? So if we do a and of that, so that would be anyways coming up to 0, because 0 and 1 is 0, 0 and 1 is 0, so that end product will be all 0. So you can see that's a power of 2. So if it's a power of say 2, any other power, say it's like something like 1 0 0 0. Okay, so 1 0 0, it's 8. Fine. So that's a power of 2. So the minus 1 would be uh like 0 1 1 1, right? So that's the 7. That's 7, we know. Now if that's 7, then what will happen? If that's 7 and we do a and of that, so and of that will be all 0. Fine. So that gives us, so this part, that's how it gives us an power of like power of 2. We are checking whether it's a power of 2 or not. Now our next check comes up whether this part here we are doing what we're checking, that whether our number is like power of 4 or not, confirming it with it. Fine. So how exactly we are going ahead with it? So what exactly we are doing, let me just erase this off, and you will see uh, fine, let it be. Now, what exactly we are doing when we are going ahead with this power of 4, this particular part? See, this particular part, this 0x then number of 5. So this is exactly we are going ahead with hexadecimal. So each of the 5 in binary would mean something like uh, 0 1 0 1, right? So that's 5 in binary. So even that's 5 in hexadecimal as well. So this is converting it to binary. Fine. Now exactly how this process works, like for each of the 5 we are getting this combination again and again. Fine. And what we are doing with it, we have a number that is 2 to the power 31. That's a huge number. And what happens to this kind of large number? In this kind of large number, like this number of breakings happens. Okay, so there can be 8 such breakings, like the number of bits can go up to that high. So if you are not sure, just go ahead with calculating that, you'll find it. So that's why we kept it 8 times 5. Now for a small number like 2, let's go ahead with like something like 0x 5. Fine. For a small number like 2, we are going ahead with this. Fine. Now for 0x5 we simply have 0 1 0 and 1. Fine. If we're doing a and of that, fine, what we will be left with? Look, if we're doing a and of that, what we will be exactly left with? We'll be left with nothing but 0, all in 0, right? That's what we saw exactly right now. So all in 0. And if we are, if it's something like 4, so if like we're doing an and of 2, number 2 itself, we get all 0. But say it's a power of 4, power of 4, as if say we went ahead with number 4. So what's the number for binary number 4? So that's like 0 1 0 0. Fine, that's a binary number 4. And in that, what will happen? I will like we'll do a and with this 0x5, and this is a hexadecimal number. So what will happen if we do a binary like and with that? So it's like 0 1 0 1. See, what's the answer to us? The answer becomes 0 1 0 0, because we're doing an and will only work when both the numbers are same. Okay, now that's what we end up having. Fine. If you're doing it with 16, you will find, like if you're doing exactly with 16 also, you will find that you have a number something like one like 10,000, like 1000. If you have 16, so that will end up after this operation, like after doing the add, you will have something. So the idea is to check that if we're doing an and of that, the number remains the same if it's a power of 4. If it's not a power of 4, the number changes to all 0. Fine. So the number remains same if it's a power of 4. So thus we can see clearly that our target is to find whether if we do a bit masking with 0x5, uh, then whether our number remains same or not. If it remains same, we know it's same. We got a power of 4. First, we checked that it's power of 2 or not. So that's a first check for us. The power of 2, I'll explain it to you. That this is how this power of 2 works. We check it with the number and the previous number. We do an AND of that, and that becomes a 0. So that means it's a power of 2. Else, it's not a power of 2. So this is the whole idea in this type of concept, and you already saw that this concept goes ahead with this kind of approach. We can go ahead with 1 millisecond solution. Now there's something you need to understand as well. So there are like this particular 0x5. So I will explain one more time in this particular, because there's a lot to know from that 0x5. Okay, so what happens in this kind of numbers when we go ahead with numbers like 0x5? So this is called a bit mask. Okay, so 0x5. So the number of fives ahead of it, defines the total length of the binary, like how many 4 bits should be there. Like for each 5, there will be something like 10. Sorry, not 10. Like for each of the 5, there will be something like 0101. Fine. For each of the 5, there's a digit like this being created. Now what happens when you have something like this like this kind of bit masking? This helps us like mask all the even places in a bit, and gives you the odd bit places. You are doing an AND operation, and this masking gives you all the odd bit places. Fine. Like the odd bit you have. And there's another one. The another one we call 0xa. Yeah, even you can repeat the number of a. Remember, this is a hexadecimal number. So a is something like, we know 1010. Fine. So when you do 0xa, so that gives us a masking of like masking of all the odd numbers and like odd places bits, and this returns us like even places ones. Okay, like even places ones we have. So this gives us the even places ones if we need that. This gives us the odd places ones if we need that. So that's a way we do masking in bit masking, and this helps us in getting or checking whether our bits are like we are getting our desired answer or not. So that's the idea. Fine. So that's how we went ahead with that. So that's a pretty easy and simple idea we have. Okay, now there can be another approach. See, this is the fastest solution you have. Now there obviously can be another approach where we simply check for the loops. We go ahead in a loop and we keep checking for like exact value, or like keep checking for uh, the value that we want to get. We start from 1 and keep checking the till the number. So that's a huge loop we keep on uh, going at. Or when there is a loop, you can obviously think of there can be uh, a like recursion way also. So we keep on checking that. So I'll just paste a code over here, so that would be much easier to explain you in terms of recursion. Fine. So yeah. So if you just look over here, uh, yeah. So how this recursion is works on? Say you have a stuff like this. If n is 1, return true. You know that. If n is like n mod 4 is 0, so we are checking the remainder. Okay. If we are dividing the number, and we are checking the remainder, that if it is divisible by 4 or not. Okay. If it's divisible by 4 and n is not equal 0, like if n is 0, then we know that it will be divisible by 4. So we are checking that if n is divisible by 4 and n is not equal to 0, then we are doing something like n by 4, just dividing the number. And in case it's not divisible by 4, we return false. Okay, and if we keep dividing the number, it will end up ending in n equals to 1. If it ends up in n equals to 1, we return true. So that's a recursive way, and this may not be the fastest way because you are going ahead with the recursive and the stack calls are done. Okay, so that's the idea behind this. Also, you can implement the same thing in terms of like a loop as well. When there's recursion, you can obviously implement that in terms of loop. So that's the whole idea of the concept behind this video. So I hope I can make you understand how this concept works, and that's more or less the crux of this video, guys. So that brings us to the end of it, and thank you for watching this video. Hope to see you soon in my next video as well. Make sure to comment down if you have any doubts related to question. I'll be happy to help you out with that as well. So thank you all for watching this video.